Okay, so welcome to our course on the fundamentals of attosecond science and technology, brought to you from the IITs at Chennai and Tirupati, IIT Madras and IIT Tirupati. So, we are now in the third session for this module on nonlinear optics in a nutshell. So, we have introduced this additional text by Robert Boyd, nonlinear optics, whereas we have the other texts that we have been referring to. One should still keep them from the perspective of this course. Of course, by no means am I asking you to master 5 textbooks in a 12-week course. It's certainly not, that's certainly not the idea, but this is an endeavor to like introduce you to key sources of primary information which have been vetted for decades now in some cases and have stood the scrutiny of time. So, it is something that one could carry forward when one takes this hopefully up more seriously or with greater intent in a future career endeavor. And of course, always credits to Professor Trebino, right. So, we will quickly look into what we discussed yesterday, which is quite a pertinent discussion from the perspective of introducing nonlinear effects in optics. In order to do that, since there is a sort of genesis of the interaction of light with matter, which we must consider really carefully, so that we place the so called nonlinear part of optics in the right perspective and in its rightful place. So, let us come back to looking at the physical origin of refractive index, which we delved into quite a bit yesterday. I will only point to the fact that when light when an atom encounters light or it interacts with matter, the simplest model is that of the in this case the electron cloud being set into dipolar oscillations, and a part of the beam is absorbed and a part of the beam is simply refracted, or refraction is modification of phase. As we saw, indeed the two aspects are related through Kramers-Kronig relationships, which classic texts on electromagnetism deal with very nicely, such as Jackson or could even be Griffiths and others. And then if one measures the absorption spectrum of light, sufficiently broadband source through a gas of atoms, then you get a very nice spectrum. Each of these lines corresponds to physiological color that we are used to perceiving through the human eye. So, this is a visible spectrum, but there are of course other regions of the electromagnetic spectrum where we can have lasers and the kind of sources that we are going to be interested in this course. Now, we looked at the fact that light sets up oscillations of the electron cloud in matter, and the simplest way to deal with this is a harmonic oscillator to describe the displacement of the center of the charge of the electronic cloud with respect to the center for the positively charged nucleus, whose inertia is about a factor of 2000 or more greater than that of an individual electron, or even a collection of electrons is not going to be significantly much heavier, but the point being that the nucleus can be considered as fairly stationary or performing indeed a very small relative displacement, if at all. The displacement of the center of the electron cloud away from the nucleus is xe, and then we solve the differential equation here, which contains the driver, the electromagnetic field at a frequency omega, and the harmonic oscillator which this field is driving has a natural frequency, eigen frequency, or in this case a resonance frequency of omega naught, and a damping factor gamma. So, if we solve for x of t, x sub e to denote that it is the excursion of the electron cloud with respect to the nucleus, then we get two terms. One is we get the electromagnetic wave back in this expression, but then we had the prefactor which was just E earlier in terms of the driving force, the Lorentz force. Here now in the solved equation for the trajectory or the displacement of the electron, we have E by m of the electron divided by omega naught square minus omega square minus 2 I omega gamma. We explored this in great detail in the previous lecture and found out that when we have oscillations which are in which the driving frequency omega is much less than the resonant frequency, underdamped oscillations, then the electron cloud vibrates pi out of phase or 180 degree out of phase with respect to the light wave. When it is much greater, omega is much greater than omega naught, the two are in phase, and when they are at resonance, the electron cloud vibrates minus 90 degrees or minus pi over 2 out of phase. This was an important sort of lesson, and a visual kind of would look like that. Okay. So, pi out of phase, minus pi over 2 out of phase, and the third thing is the 2 in phase, while the omega much lesser than or much greater than omega naught cases have modest or weak amplitudes. There is a strong vibration amplitude on resonance, because the factor that divides everything is just 1 over gamma, which is much smaller than omega in our considerations. Or we could have a nanoparticle with a whole set of electrons and many charge centers or ionic centers clustered together, also being subject to similar oscillations. So, we looked at the atom's response, which is approximately complex Lorentzian, by introducing a dephasing factor between the natural frequency of the atomic system and omega, the driving frequency or the driver's frequency. Delta is the detuning variable and gamma is the damping factor, if you see. So, introducing these factors and making the assumption that omega naught plus omega is approximately 2 omega, they are pretty close, especially as compared to omega gamma, which is in the next term, but we do not throw away omega minus omega naught to be 0, it is delta, the detuning, the variable of interest in this problem. Then write this in terms of the real and imaginary parts, as we have done here, and we get we can look at the fact that the real part is an even function of the real part is an odd function rather of delta, whereas the imaginary part is an even function, and this is how they look. And this answered the question of what, so far this is what light does to matter. We also examined what matter does to light, and which is where we kind of stopped at some point. Okay. What matter does to light is the next aspect of this light matter interaction. So, light does something to matter and matter does something to light, that is the interaction. So, it is indeed a good conversation, not a monologue between the two protagonists in this case, right. So, we looked at the fact that at every plane in the medium, light emitted from the excited atoms interferes with the incident beam. So, it is indeed a good idea of how this is happening is to consider the fact that, say, an infinite, say, monochromatic like beam in steady state is propagating through this medium, and at every point the interaction of these of the light beam with matter sets up oscillations of the electron cloud, and those oscillations result in subsequent radiant emission, and at any point the total electric field is the sum of the incident radiation plus the sum of the electric field of the incident radiation plus that of the emitted radiation. Of course, there is the magnetic field, but we must always remember that we are prejudiced and biased towards the electric field, because this is a much stronger interaction in normal materials. If you had magnetic materials, magnetically sort of, I may say so, active materials, one would also have had to consider them the magnetic field, but we are not going to do that for a good part of this course. If we do, then we will make a specific mention of that, right. So, Maxwell's equations will allow us to solve for this total field at any point. So, if you are surprised by the fact that we have the incident and the emitted field summing up to give the total field, It is also not that I can separate these two out and in materials measure this separately. No, no. E is what you measure and E is what you have. These are two components to it. Okay. We are going to formalize this in the constitutive relations of Maxwell's equations. However, a good example of this happening in a macroscopic element is a wire grid polarizer, where randomly polarized light with electric field vectors along some unpreferred along all directions without any preference on the transverse plane, that is a plane transverse to beam propagation. When this light passes through the wire grid, which has in this case wires in the grid going in and out of the plane of the board or the plane of the screen here, the light that is emitting out of this essentially is in the direction perpendicular to this wire grid, because electrons oscillate along this wire in and out of the plane, and the radiation emitted by the electron, the electric field of the emitted radiation is pi out of phase with that of the incident field, and hence these two efficiently cancel out and you basically get the polarization which is perpendicular to the direction of the wires coming out. Indeed, the cancellation is not perfect, there is a tiny remnant field which leads to a finite polarization contrast of this of a wire grid polarizer to actually wire grid polarizers are very good in terms of polarization contrast. Okay, so this is where we kind of stopped in the previous lecture, and we want to take this up even further and now understand and learn better, appreciate better what light does or what matter does to light, since we now have a good model for what light does to matter, which is a forced damped harmonic oscillator. We looked at the classical perspective of this, quantum mechanical perspective yields similar nearly identical results. So, we do not have to worry about not being good enough in terms of using a classical picture, which is all we have done so far. Now, in Maxwell's equations, we have the 4 equations containing now 4 fields E and D, the electric field and its counterpart D called the displacement vector or the field of the displacement vector. We have H and B, and we also have free charges, free currents, which we can even neglect for a good part of this discussion. Okay. Please accept my apologies for these typos which crept into this equation, but we will come to that. Essentially the constitutive relations of the that go along with Maxwell's equations, these are the equations for that take care of the modeling of the media, right. So, these relate the electric field of what you may consider the incident wave, the primary field, that is to say this field would be present whether or not the medium is present, and in the medium the field that we are concerned with in terms of the electric component is D, and D is a sum of the primary pristine, you can call even incident field, plus capital P, P being the so called polarization vector. Okay. So, now the name polarization is a little unfortunate because we have a certain connotation for polarization in optics which we are using regularly. So, this is not just polarization, we should call this the polarization vector. I hope my phone does not ring. I will make sure that it is in silent mode. It actually is not, so it is good to do that. Okay, so the polarization vector P is essentially the dipole moment per unit volume at every point of interest that we are considering. It essentially concerns the dipole moment per unit volume in a block of matter, okay, at any given point of interest inside, but you could also consider points outside where there are 0 dipoles per unit volume. Okay, so, that is the vector p. Now, we need to complete the loop in this case by building a good model even for the polarization vector. I will simply refer to this as the polarization henceforth in short. So, the point that we want to be aware of and make here is that the polarization vector is also a function of both spatial and temporal variables, okay, just in as much as E, or for that matter D, are both functions of space and time, likewise H and B. The point that we should appreciate here is that we need, in order to complete the loop, as I say, a relation between P and E, because what are the fields we know initially? The field that we are applying to matter, the field we are applying to matter, okay, let me just do it differently. The field being applied is E. So, in this sense it makes a lot of sense to consider this to be a scenario of this type, where you can say that, hey, I have a parallel plate capacitor, and in between it is filled with some medium. Okay, so, obviously, the medium in this case has to be a dielectric, and onto this we apply an electric field aided by the capacitor, and that field gets modified inside the medium. So, this is E, and the field inside is D. At every point you have a P. So, now what we know is E, it is in this sense that E is the primary field, and we do not know P. So, how do we solve the problem or close the loop, as I am fond of saying. So, we have to have a physical and hopefully simple, if you wish, model for P, the unknown, yet unknown, to be written in terms of the only thing we know, which is E. So, E is what we know, P is what we do not yet know. So, when we encounter a scenario like this, what can we do? What is the only thing we can actually do? The only thing we can do is P Taylor expand in E, the known variable, our go-to trick. We did this for pulses. So, we do exactly that, but we note that P is a vector. So, if I simply write this equation in a component form, that is just the equation. The simplest assumption, the simplest form in which I can write P out in terms of E is to consider a linear relationship between P and E. Okay. P linear in E. Remember, these are 3 component vectors, okay, Pi and Ej. The even so this is the simplest consideration in terms of how P scales with E, but this is not yet the simplest. We can still go a step further and simplify things and say that if Px, if I take a Cartesian coordinate system, then the vector P has 3 components, Px, Py, Pz. I can make an even further simplifying assumption, and it is an assumption which needs justification, that Px depends only on Ex, Py depends only on Ey, and Pz, sorry, that is a typo or a righto. Pz depends only on Ez, and that all these 3, while being proportional, while the proportionality is established, Pi is proportional to Ei, but then I go a step further and say they are all related in terms of writing down a proportionality constant by the same proportionality constant. I could well have had a scenario where we had Px related by chi x to Ex, but Pz related through a different number chi z to Ez, albeit for the same medium. So, in the most general scenario, preserving linearity would have been to have Px being related to Ex, Py being related to Ey, and Pz being related to Ez through 3 numbers, a set of 3 numbers, chi x, chi y, chi z, chi 1, chi 2, chi 3. We could well have had this scenario, but in the most simple case, chi x, chi y, chi z are all three of them are equal. This is an assumption, it is not necessarily true. We have no right to insist that it is necessarily true. It is just that I have supposed it so I can write this equation down quite simply. Okay. So, if this equation which I have written down here this equation assumes linearity and isotropy. Oh, okay. Isotropy because the coefficient for the 3 eigen directions x, y, z are all three of them are equal. That is isotropy. Okay, we can go a step further and ask, for example, why can't Px, why shouldn't Px depend on Ey and depend on Ez also in the most general case? Okay, so indeed it can. That would be the most general case, that Px depends not only on Ex but also on Ey and Ez. Py depends not only on Ey but also is cross linked to Ex and Ez. Pz depends not only on Ez but also on Ex and Ey. Okay. In which case, while everything remains linear, we would have had to cast this most general linear scenario still within the domain of linear interaction. We could have cast this to be P1, P2, P3, E1, E2, E3, okay, to be related through a matrix of 9 entries chi 1 1, chi 1 2, chi 1 3, chi 2 1, chi 2 2, chi 2 3, chi 3 1, chi 3 2, chi 3 3. Okay, where 1, 2 and 3 correspond to x, y and z respectively, or we could have chosen a different coordinate system, different, you can say ortholinear coordinate, curvilinear coordinate system too. Okay. But then let us stick to Cartesian for the sake of convenience. We would have chosen a different coordinate system for reasons of geometry and symmetry, but nothing prevents us to put our entire effort in doing things in a Cartesian coordinate system and visualizing things that way. But while that is the case, okay, this is the most general case, which is what gives us the relation. If I write these matrix, this matrix relation in a compact form, then P I is simply chi I j E j, where I and j take values 1, 2 and 3, and we sum this over j, but using the so called Einstein summation convention, I can forget about writing the summation symbol and simply say that an index that repeats itself in a term implies a summation over that particular index and so on. Just mathematical convenience, you can always write the summation symbol if you so wish, but we have used the summation convention here. So, any index that repeats itself implies a sum. So, this is behind writing this expression. Okay, I have disregarded an epsilon naught here. So, pardon my neglecting that, but the point is nonetheless equally well made. If you like, you could have absorbed the epsilon naught, which is the universal constant, into the definition of chi, but let me not make things confusing. So, the epsilon naught is explicitly left out there, but the whole point being that for linear interactions, chi is a rank two tensor.